Hello, in this video we're going to go over problem A1 from Putnam 1992. So this is a functional equation problem. So how do we deal with functional equations in general? So the way we deal with functional equations is we start with the equations that are given, usually one equation. In this case we are given multiple equations, and we plug in different values, we play with them, see what we can get out of it. And in this case, in fact, they also told us what the function is. So let's first read the question and then we'll get to the details of that. Prove that f of n equals 1 minus n is the only integer valued function defined on the integers that satisfies the following conditions. So this function f is from integers to integers, and it satisfies these three conditions, and we want to find out what this f of n is. And in fact, they told us that f of n equals 1 minus n is the only integer valued function satisfying these. Okay, so the first thing I would do is I would look at this equation, and I would see that naturally, because the first one tells you f of n equals n, it makes sense to take the f of the first one and then use the second one and then use the first equation. So if we take the second equation and take f of that, that would give us f of n plus 2 equals f of n. And this is gonna be my scratch work, so I'm gonna write it down in a different color. Now, I know that f of n is n, so that means the inside, the two f's basically cancel each other, and the inside comes out. So we get this. Now, this is quite interesting because it tells us that if you have f of n, you can get f of n plus 2. And if you have f of n plus 2, you can get f of n. In other words, we know if you look at the integers 0, 1, 2, 3, 4, 5, 6, and on the other side -1, -2, -3, -4, etc. We know what f of 0 is. So from here we can get f of 0 plus 2, which means we can get f of 2. And then from here we can get f of 4, and then f of 6, and so on. But at the same time, we can also go backwards. If you know f of n plus 2, then you can get f of n. In other words, you can subtract 2 from that. So from here, you can get to -2, and then from here, you can get to -4, and so on. So it looks like we would have to use some form of induction to prove this for even numbers. But the question still is not completely and fully answered, because that only answers the question for even integers. How about odd integers? In order to get to odd integers, the idea would be the same, but you need to have some initial term, something that if you can find that, then you can use that to find everything else. So how do we find the first one? Well, we are given some initial value here, f of 0 equals 1. So why not use the first equation again, f of n equals n, and see what we get. If you take f from the last equation, f of 0 is f of 1. And we know that f of 0 is 0, so f of 1 is 0. So once you have f of 1, then you can get f of 3 using the equalities that we found. Then you can get f of 5, and then you can also go backwards. So once you do that, then you're done. Now, how do we articulate that and put it on paper? So let's write it down. Whenever I'm solving functional equation problems, I make sure that I keep my work really clean, because it's very important to be able to refer to the things that have been done in the previous steps. I often write it down as step 1, step 2, or maybe claim 1, claim 2. If you want to write it as lemmas, just in a way that it is very organized, it becomes easy to follow. One of the key facts that we keep using is f of n plus 2 is equal to f of n. So this is the first thing we are going to prove. Okay, and you can either write it down like this and say claim 1 and I'm going to prove it, or you could get to that and then call it equation 1. In some ways you would have to identify that so that you can refer to that later. Okay, so first note that by 2, if you take f from the second one f of n plus 2 is going to be f of n by the second one. So I'm taking f from the second one. Now by 1, f of n plus 2 is equal to, you can take out the two f's. The two f's basically cancel each other. So that becomes f of n plus 2. So that means f of n is equal to f of n plus 2. I'm going to call that star, and I'm going to refer to that in the next steps. Now we determine that since we have these, we would be able to identify all the even ones, and then we can also identify the odd ones. But how do we articulate that? We would articulate that by using induction. So we prove by induction on M that f of even numbers 2m is equal to 1 minus 2m for all integers m greater than or equal to 0. So that's what we're going to do. Okay, so basis step. Basis step would be f of 0. F of 0 is 1, that's given, which is 1 minus 2 times 0. So that completes the proof of the basis step. Inductive step. Inductive step, suppose we know the equality. Suppose f of 2m is equal to 1 minus 2m for some m greater than or equal to 0. F of 2m plus 2. So we're going to look at the next step. That's f of 2m plus 2. This is equal to. So we're going to look at the equation star. This is f of 2m minus 2. This is by star. I'm referring to that equation that I got before. This is equal to 1 minus 2m minus 2. This is by inductive hypothesis. By inductive hypothesis, f of 2m is 1 minus 2m. And that is 1 minus 2m plus 2. So this completes the proof by induction. So this shows f of 2m for every m greater than or equal to 0. Okay, so that's the first step. Then we will show by induction that f of negative 2m is also 1 plus 2m. So now by induction on m, we will show f of negative 2m is 1 plus 2m for all integers m greater than or equal to 0. Again, basis step is obvious. F of 0 is 1. That's given. So inductive step. Suppose you know f of negative 2m. That's equal to 1 plus 2m. If you look at f of negative 2 times m plus 1, that would be f of negative 2m minus 2, which is going to be, this is by star. You can write it down as if n is negative 2m minus 2, n plus 2 becomes negative 2m. So this would be f of negative 2m and then plus 2, which is equal to 1 plus 2m plus 2. This is by inductive hypothesis, which is equal to 1 plus 2m plus 2. So therefore, we showed this equality. Therefore, f of n is equal to 1 minus n for every even integer. Okay, so we showed it for even. Now we will have to show for odd integers. So now by 1, f of 0 is equal to 0. That's given, which means f of 1 is equal to 0. Now, the rest is quite similar, so I won't even worry about writing it down. So now, using star and induction, we can similarly show f of n is 1 minus n for every odd integer as well. Therefore, f of n equals 1 minus n is the only solution. Okay, that brings me to the end of this video.